Yeah, please go ahead.
Okay. Good evening, everyone. Uh, Myself, Dr. Chandrabhushan Pal, FDP coordinator. It is my privilege to introduce our esteemed speaker, Dr. Vaibhav Goud, sir, who has graciously accepted our invitation to be with us today. Dr. Vaibhav, sir, holds a PhD from IIT Kharagpur and has made remarkable contribution to academia and research field. With a distinguished career in education, he previously served as an associate professor 2014 to 2018 and assistant professor 2009 to 2014 in the Department of Chemical Engineering at IIT Guwahati. Since October 2018, he has been serving as a professor in the same department. Dr. Vaibhav sir research is recognized in international journal with over 125 published research articles, 15 book chapters, and one authored book. He has presented papers at more than 40 international and 80 national conferences, showing his impactful contribution to this field. Beyond research, Dr. Vaibhav sir has a strong track record in mentoring and supervision, having successfully guided more than 10 PhD scholars in their academic career. We are truly honored to have him with us today, and we eagerly look forward to his insight. Let's give a warm welcome to Dr. Vaibhav God sir, and today's session to uh, take the Dr. Vaibhav sir. Thank you.
Thank you for the brief introduction. Before we begin with this talk, let me first give you the glimpse of today's talk and why I have selected this particular slide. Because as this particular program is related to food processing technologies, so I thought of like just giving you the glimpse of what we are doing here in IIT Guwahati in terms of food processing. As we are already running one international joint master's degree program in the food science and technology here, this program is basically a joint program between IIT Guwahati and the Gifu University, Japan. And the associated department in this particular program involves chemical engineering, biosciences, bioengineering, chemistry, and the School of Agro and Rural Technology as well. Because as you know, this particular field of food processing is interdisciplinary. So as a matter, we always need to have some kind of expertise from the chemical engineering, the biosciences, chemistry background as well, and then agro and rural technology, which is the basic of this particular field. So with this particular thought process, we initiated this program, and we are successfully running this program since 2019. And although the intake capacity is not much in this particular program, but still since last 5 years, we get a very overwhelming response for this particular program. We get a lot of applications, but due to seat limitation, we are not able to match to the requirement of the some students. So that is one small limitation of this particular program, because as you know, it's a joint program, so we cannot increase the seats to a marginal level. Like we cannot go very high intakes in this particular kind of program. So this is the brief about our department. And as it has been told already that I belongs to Department of Chemical Engineering. So we are hosting this particular specialization, that is, sorry, food science and technology as well. So I thought let us continue with this particular topic only then about the food processing. So wherein I also work in the area of the supercritical fluids. So I thought of covering this particular topic in the today's session and give the glimpse of this particular topic and its importance in the food processing and what we have done in the past in this particular field. And also currently we are working on this particular topic as well. So as you know, this industry segment in the food processing industry, it basically comprises of these following segments. As you all know, because most of you belongs to this particular food processing background only. So the fruit, vegetables, the dairy, meat, poultry, and marine, grain, seeds, packaged foods. That is including the beverages also, right? So if you see on this particular right side of this here, which shows the distribution as well, like how it has been distributed across this segment. That is basically a percentage relative share of these various food segments in the food processing, where you can see the packaged foods, the grains, and the dairy is significantly high, right? Then the fruit vegetable is very minimal, that is 2%. Poultry, meat, dairy, and marine is close to 10%. So one can imagine like the kind of these segments are distributed in these particular segments, right? So why this particular topic is important? Because as you see with the current lifestyle, as then also most of us like very health conscious, so we always try to go for the very good quality food. Then we are discussing about the separation processes. So this separation process also plays a good role in the food processing industries as well, because this particular chart here, this graph, it shows you the different processes. For example, the processes which are being used over the years in the industries, and the special processes which are getting attention nowadays because of its, I can say, advantage, or maybe say positive impact in the separation. So if you talk about the top one, that is distillation, it is the most widely used technique in the industries for the separation purpose, right? If you all agree to that. And also the in terms of knowledge, it is a very well understood process in the industries, and because of that, it is the most widely used process in the industry for the separation. And then if you see that ladder down till the liquid membranes, so from the distillation, then absorption, crystallization, solvent extraction, and these are very well-known processes in the industry for the separation. But now the special attention is there because of certain regulations in the utilization of these processes. So now some switchover is also happening, and then now some special processes are also taking special attention. And because of that, we'll be discussing about the special processes as well, which includes the extractive and the azeotropic distillation. This is also, as you know, it's a very widely used, because azeotropic distillation we know, but then extractive and then the azeotropic distillation, this is one component now. It is being practiced nowadays, where you can do both the things simultaneously. And the research is also going on in this particular direction to improve the process efficiency as well as to improve the separation efficiency as well. Then the absorption, like using the liquid feed, the membranes, like the gas feed. And now if you see here, the red one that indicates the supercritical extraction. So this supercritical extraction is having a very important role in the food processing as well, because of its green tag, that is a greener process, and also it is very critical in terms of separation of the compounds, right? So because of that, this supercritical extraction is getting a lot of attention nowadays in the food processing, and there are many successful plants running across country as well regarding the extraction of some essential compound from the food matrix. Then the chromatographic separation, as we know, the field induced separations is also there, that is the plasma based. Then affinity separation is also there. But then the knowledge and the uses of this particular technology is still limited because of the many other factors involved in this. As you know, because of the cost factor, because of the you can say the scalability, and other factors are also involved in that. And hence, because of that, these processes, although in terms of knowledge are well understood, but in terms of uses, still does not reach to that wider uses so far. But now, with the time, obviously, it will be used in the industries with a wider extent even. Why there is a need for this particular technology? Because rather than giving the chart, I have put it in the form of the bullet points so that it will be easy for you to understand as well. Why the supercritical technologies is very essential nowadays. Because if you try to see about the extraction or maybe the isolation of the natural product from any kind of bioresources, or kind of, you can say, the different vegetative elements as well. This has been done in the past using the organic solvents, right? But then, as we know, with the time and because of these industrial regulations, changing regulations of the industries, these traditional based extraction technologies are now facing a lot of challenges. And these particular solvents also cause hazards to the human health. because if the stress of the solvent remains, which becomes a matter of concern to the human health as well. So with this increasing concern about the environmental pollutions, and as you know, these solvents always pose environmental hazard as well. So there is always there is alternative to find out the some alternative solvents, or you can say the greener processes to the existing technologies. And then because of these strict regulations, so this demand of these kind of supercritical food extraction technologies are increasing nowadays. Why it is so? Because these processes, these supercritical technologies are very safe. Why I am saying processes? Because in these processes we can use a different solvents. It is not defined for a specific solvent. But as we know, mostly they use a supercritical CO2 as a solvent. But now a lot of research is also going on using supercritical water technology as well. So that I will be discussing anyway during the course of this presentation as well as this talk, that how these two techniques are different, because we worked on these two techniques in the past. And the advantage is like they use very clean, this is a very clean process, safe and inexpensive as well, because if you are using water as a solvent, then it is mostly inexpensive material for the extraction. The non-flammable, that is one of the most significant advantage of this particular process. Non-toxic, because water and the CO2 both are non-toxic, and then also because of the environment friendly solvent, as CO2 and water both are environment friendly solvent, so it doesn't pose any kind of hazards to the environment. So because of these advantageous nature of this process is being widely used in the food processing now. So I need not to go in the detail about what is supercritical fluid, because I hope most of you know about this particular supercritical fluid and what exactly the and how exactly it is termed as a supercritical fluid. But I will just brief you about this particular concept in a very short manner, because the any solvent when you use, like for example, if you are using even the methanol, ethanol, the water, if you are using CO2, so these kind of materials, when the temperature and pressure of this substances it raise above its critical pressure and the temperature, because every particular solvent has a critical point, right? So once it reaches to that particular point, and even if you go on further increasing the temperature and pressure beyond that particular point, then after this particular substance enters into a supercritical state. So below that it is called as a subcritical state sometimes. So if you see the literature, sometimes it is referred as a subcritical one, because if it is below its critical point, then we term it as a range of the subcritical range of the solvent or the substance. And when it passes, or when it reaches to a critical point, then we call it as a critical temperature and the pressure. But once it goes beyond that critical point, so basically it's a supercritical now. So it has reached to a supercritical state of the particular substance. So this fluid has a advantage that it behaves both in the way of gas and the liquid-like properties, and that is what is the main advantage of this particular supercritical fluid. Although the fluid is a single fluid, but it behaves like a gas and a liquid. So basically, it means it behaves in both the way that act as a gas property as well as a it also acts as a kind of the properties of the liquid, and that helps in the extraction, because if the particular material is giving the properties of gas and the liquid, so one can imagine, like suppose for example, if I am doing the extraction with the only hexane, so the hexane is nothing but in the liquid phase, so I am doing the extraction in the liquid phase, so there is no matter of the gas. But when it comes to supercritical fluid, it gives the properties of the gases as well, so the diffusion becomes very fast, and because of that the extraction efficiency goes on increasing. So that is what the advantage of this particular supercritical fluid. And the critical temperature, basically, these are well defined terms in terms of like supercritical temperature and the supercritical pressure as well. So the critical temperature basically is the maximum temperature at which a gas can be converted into a liquid by increasing the pressure. Similarly, the pressure is the maximum pressure at which a liquid can be converted into a gas by increasing the temperature. So that because of this reverse phenomena, it helps in giving the properties like gas and the a liquid. And if you further go on increasing this temperature beyond the critical point, then these liquids get converted into a unique state of the nature, and this is called as a supercritical region in the graph. So for the better understanding, maybe I will just show you this particular graph here. So this right side of this particular block here, it shows the simulation study, or you can say the distribution of the molecules in the supercritical fluid. This is basically a simulation study. Obviously, you cannot observe this in the supercritical reactor. You require a very sophisticated technology when you have to, because with the very fine camera scale, you need to identify these phases in the reactor, right? But with the help of simulation, obviously, you can do this study effectively, because the temperature range of the supercritical CO2 is a very normal range. Even the pressure is very normal, so you can easily do the simulation of this particular solvent using the simulation work, right? So here, if you see this particular graph, which shows the solid, liquid, and the gas phase of the specific substance here. So, for example, this yellow line here, it indicates the critical point of the specific substance here, right? Now we are trying to take the example of the CO2 in this case, because the CO2 has a critical pressure of around like 7.29 megapascal, and then the critical temperature is around like 31 degrees C. So once these temperature and the pressure increases to this particular extent here, we can see that, we can say that even the the critical point of the substance has reached. Now suppose if I have gone increasing this particular temperature beyond this range, and also the pressure in beyond this range, so what happens is like this critical point get moves over it, and then it enters into a supercritical stage here. So you can see this top square here, which shows the supercritical state of the substance. So this way you can tune these properties of the CO2 just by varying the pressure and the temperature. Suppose if I have to carry out this particular extraction at the critical point, so I can specifically maintain this pressure and then this temperature, so that it can reach to critical point. If I do it slightly below that, then it will be a kind of a subcritical stage of the particular substance. And if I go beyond this particular point, it is called as a supercritical stage of the substance. So this helps in identifying the stage of the substance as well. So likewise, the graphs of different solvents have also been traced in the literature. You can easily look into it for methanol, ethanol, water, and many other solvent as well. But the most widely used fluid in the case of supercritical fluid technology is the CO2 and the water, because of its very clean and then the environmentally friendly nature. These two are the most widely used solvent for the extraction. Now, if you see here on the right hand side, the local density like liquid and the local density like gas here. So idea here to show you is like, say for example, if you see this black spot which are agglomerated at one particular location here. So this particular point, if you try to measure, so the density of the particular point is actually kind of a density of a liquid. And when you see these whites here, the other circle with a single two dotted black points here, which shows this particular region is acting as like a kind of a local density of a gas. So now, as I told earlier as well, this fluid behaves like it shows the properties of the gases and like a liquid, and that is because of this particular nature of the supercritical fluid in the reactor. So that gives a very good efficiency for the extraction as well. And further increasing in this temperature, you are just increasing the supercritical stage of this particular fluid. But beyond certain point, you may find that further increasing pressure and the temperature is not significantly playing a significant role in the extraction, because now the properties which are required to be achieved are already be achieved at that particular temperature and pressure, and further increasing of this pressure and temperature is not affecting those properties, and hence you won't see any kind of enhancement in the extraction as well. So those basically iterations we can first do in the simulation work, and then you can go for the practical work as well, or you can directly do the practicals using basic optimization techniques as well. So this is about this particular supercritical fluid and how it behaves in the reactor. So for example, in if you consider this particular small box as a one reactor, and if you add a food element in this particular reactor now, and you allow this particular supercritical fluid to allow to interact with this food matrix. So these gases, like the density of this particular voids here will try to penetrate inside the food matrix, and these liquid-like materials will try to solubilize those particular extracted material. So that's why it plays the role of both gas and the liquid properties in the supercritical fluid. So because of this, the supercritical fluid, although it is considered as a single homogeneous fluid, which is formed at the temperature and pressure above the critical point, as I shown earlier, because once you go beyond this TC value and the PC value, basically you are entering into a supercritical stage, and then here basically it act as a kind of a single phase only. So you cannot distinguish that whether this is a liquid and the gas, but just to show the nature of the substance here, I have shown you this particular box here that becomes very easy to visualize and to understand what is meant by the liquid-like properties and the gas-like properties. So that means in this particular way we can understand it very easily. But then once it reaches to a supercritical stage, it becomes very difficult for you to find out this kind of phases in the this single phase. That is called as a homogeneous fluid, which is formed at this particular temperature and pressure. And that is what is the uniqueness of this particular supercritical fluid, that although with the simulation and all you can always distinguish these, but when you try to see this particular fluid at a supercritical stage, it seems to be kind of a very homogeneous phase, which I will show you down some slides what is meant by that. And the supercritical fluids are like are heavy like liquid, as I mentioned, because if you see here, once this behaves like a kind of a liquid, so it acts as a kind of heavy like a liquid, but then have the penetration power of a gas, because once you see the density of this material is acting a kind of a substance acting kind of a gas, so because of that the penetration becomes very easy, and after penetration once it comes out, then solubilization in the heavy liquid becomes very easy. So that way it plays both the roles here. Similarly, when you talk about the supercritical fluid here, these are produced by just heating gas above its critical temperature, as I mentioned, and compressing liquid above its critical pressure. So by that way, once you try to make these two properties or two parameters in a certain combinations, it leads to kind of a supercritical fluid. So what is meant by these particular properties of the liquid gas and the supercritical fluid here? So this chart, which I have taken from this particular chapter of this textbook here, which you can see, uh, this shows the properties of the gas, supercritical fluid, and the liquid. Now, if you try to understand these three column very easily, so the density, if you see, of the gas at ambient is around this much. But when you try to see about the liquid, it is relatively high, right? But the supercritical fluid has a density in between these two. So that is another advantage of the supercritical fluid. Viscosity, it is very low in case of supercritical fluid here. Even it is considered less than that of the gas as well. That because of that, penetration becomes very easy in the food matrix. And once the penetration becomes easy, so the interaction of the food molecules with the solvent becomes very easy, and as a result of that the extraction becomes efficient, right? Whereas in case of the viscosity of the liquid, if you see, it is quite high. Similarly, about the kinetic viscosity, the thermal conductivity, it is the maximum in case of the supercritical fluid, because these are all of the reported data. Then no need to cross-check this data as well, because this has been cross-validated by many scientists in the past as well. And if you see the diffusion coefficient as well, so the diffusion coefficient is also one of the important parameter for the supercritical fluid, and it has a very good diffusion coefficient. Because of that, the diffusivity of this particular solvent is very high in case of the supercritical state. So as I mentioned, the supercritical fluid, it has the properties like intermediate to those of the liquid and the gaseous state, because if you see these columns, it makes you very easy to understand how these properties are intermediate to that. In some cases, the properties are far better than that of the intermediate as well. But the important properties, basically, these are nothing but in between. So uh, and just because of that, these are also known as the compressible liquids or the dense gases, and that helps basically in the extraction. And the higher solvent power of this supercritical fluid is mainly due to their liquid-like density, and that is what I have shown in the simulation here. Though the liquid-like density is very significant and the important parameter of the properties of this particular supercritical fluid. Because of that, the solvency, or you can say, because in supercritical fluid they always term it as a kind of a solvency power of the supercritical fluid, that is called as a solvent power of the supercritical fluid, is mainly because of this liquid light density of this gaseous mixture. Okay, and that is resembling in the simulation as well, which you can see here in the course of the study. The excellent transport properties, because as you know, it's behaves like a gas-like viscosity, so the transport becomes very easy in terms of the penetration of the gas into the molecules, and it is like around 10 to 100 times less than the liquid, and also has a gas-like diffusivity, which I already mentioned. The diffusion coefficient is very good for this kind of fluids, and zero surface tension, which is a very unique property for this kind of the fluid, because the liquid always has certain kind of surface tension. But when you talk about the supercritical fluid, the surface tension is nil. Basically, it's a zero, and that becomes a very essential property for this particular extraction as well. Now, the critical parameters of these common fluids, if you see, because always we try to see the density as well as pressure and the temperature as the critical parameter for any kind of fluid when you are trying to use in the supercritical system. For example, like CO2, when you are using CO2, its temperature, as I already mentioned. So the density, if you see here, is like close to 0.47. So one can imagine the density of this particular fluid and compared to that of the water, right? Even if you try to compare the density of the supercritical water, it is even far less than that of the CO2. And because of this nature of this fluid, this water is also acting a kind of a very good solvent for the supercritical extraction. And a lot of work is also going on in this particular field, not only limited to food processing, but other applications as well. But CO2 mostly it is being used in case of the food processing, but water has other application as well, not limited to a food processing only. And other solvents which are listed here can also be used as a supercritical fluid for the extraction purpose. But then for the, you can say, environment friendly nature, as well as to understand the food processing part of it. So mostly CO2 and H2O being studied widely. So why the CO2 is the most commonly used, as I already mentioned, in the food processing? Because it is inert, non-reactive, right? Inert means it's non-reactive, inexpensive, easily available CO2, odorless, it has no odor at all, tasteless as well, and environment friendly. So E stands for environment friendly solvent and has very low energy input. Because of that, this is being preferred or even the water supercritical fluid. And there is no solvent residue in the food after the extraction. That means when you try to do the supercritical CO2 extraction using the food matrix or in the food processing, so you cannot uh, see any traces of solvents left over in the extracted food matrix, because once it reaches to room temperature, the entire CO2 becomes a kind of a CO2 gas, and it comes out from the food matrix automatically. So that is what is the advantage of this particular fluid as well. And it is suitable for the non-polar substances and thermolayable natural product as well, because some compounds are very heat sensitive, so you cannot extract those particular some specific compound from those particular natural substances. So on such conditions, you have to always rely on the supercritical CO2 technique, because the temperature, if you see, it is close to only 31 degree to the max. Even if you want to increase it, you can go up to 50-degree, because beyond that, any alteration in the temperature and pressure will not have any significant change in the properties of the CO2 as well. So the maximum you can go up to 70-degree, not more than that. So such substances which are thermal sensitive or the heat sensitive can also be extracted using this particular solvent. Apart from that, non-polar substances, as I mentioned, because of the non-polar nature of the solvent, it can extract this particular material very easily. So this is basically the point I was just discussing in one of the slide earlier, that critical properties of the CO2 and the H2O, how, if you have to compare, you can compare it here. For example, critical temperature, the critical pressure, and then the critical volume of this particular material per kilomole. That can be also seen here. And if you try to see this particular bottom graph, which shows how this liquid and the gas phase gets mixed with increasing the temperature and pressure over the period of this graph here. So this can be explained in a very logical way. I will just explain in the logical way in the next slide. But if you can see here, this particular first uh, point here, which shows this black line, right, which indicates the bottom one is nothing but the liquid CO2 and top portion is nothing but a gas. Gas in the sense is like portion in the reactor. Now with the temperature and increasing pressure, if I go on increasing this particular temperature and pressure here, we can slowly you can see that this black line, which is basically differentiating the gas and the liquid state of the material here, which is getting dissolve. And once it reach to a supercritical state now, you cannot see this particular line here, which shows that it has reached to a gaseous state, right? Because it's very difficult to visualize this particular phenomena here once it reaches to a supercritical fluid, because you need to go for very sophisticated cameras and system here to visualize such kind of behavior of the molecule here. But with normal lenses, we cannot analyze those particular things. So, but here just to show this way it changes the properties of this particular substance and forms a very homogeneous phase here. Now you can see you cannot distinguish where is the gas and where is the liquid. So this I can show in the stepwise manner here. So basically here, if you see, we can see the separate phase of the carbon dioxide here. So this is basically a carbon dioxide. This bottom portion is a carbon dioxide, and this is basically empty space on the top. And this meniscus is easily observed here. Now with a slight increase in the temperature, this particular layer begins to diminish. Now we cannot, although you can see a small layer here, but some part of it already got converted into a gas, right? Now, if I have further increased the temperature, which causes this gas and the liquid densities to become more similar now, and then now with this increase in the particular temperature, the meniscus is less easily observed, but still it is evident because you can still see this particular line here, which shows that still there is some presence of the liquid CO2. But once it reaches to a critical temperature and the pressure, so this phase shows the critical temperature and the pressure have been reached here. The two distinct phases of the liquid and gases are no longer visible. You cannot see any distinct phase of the gas and the liquid here now. It is completely a homogeneous mixture, that is called as a one phase mixture here. And once it reaches to such kind of a state, that is called as a supercritical fluid state of this particular substance here, where this particular substance now behaving or shows the properties of the both liquid and the gases, which are shown in terms of the simulation as well, right? So although you cannot distinguish here now the gas and the liquid, but this substance once it reaches to a state of supercritical, it behaves in that particular way of liquid and the gases. Why it is very important to understand these properties of this supercritical CO2, because if you try to see the density of this supercritical fluid, it depends on temperature and pressure, as we know, right? This is a very common concept, and it varies also in the range of this one. So now because of this critical point, if you try to vary this supercritical stage of this particular substance, obviously there will be a slight variation in the density also will takes place, and because of that there is a range is given here, not a specific value. So once I change the critical temperature and pressure, obviously there will be a slight change in the density, but if you see there is a upper and a lower limit also, so beyond that it will not go. So if you do any alteration in the temperature and pressure, it will not change further. And that's the reason I mentioned once it reaches to a certain level of the properties, further increase in the temperature and pressure will not play any role of change in the properties of the supercritical fluid as well. The supercritical CO2 density is significantly lower than that of the density of the liquid because we know the density of the normal liquid is this much. Now you can imagine the density of the supercritical fluid which is given here in this range. So one can understand easily like how effective this particular supercritical fluid is in terms of the density parameter. And the transport properties of the supercritical fluids are those between the liquid and the gases, because as I already mentioned here in the one of the slide that because of the densities of the liquid and the gases, this particular fluid act as a kind of a homogeneous phase, and hence it imparts the properties of both liquid and gas, and that helps in the transport properties of the supercritical fluid as well. The viscosity is 0.05, you can see here, right? So which is significantly lower even than that of the hexane, because if you try to see the viscosity of the hexane than that of the CO2, one can easily understand that how it is effective in terms of extraction, because its viscosity is very less, and that is the prime basically you can say the parameter which we always try to consider while selecting the solvent for the extraction, that the viscosity should be low, and that's the role of supercritical fluid here. Because of its low viscosity, it gives a very effective extraction or extraction efficiency as well. And the molecular diffusivity, which is one order of magnitude higher than that of the diffusivity in the liquid state, and that helps in the extraction, because if the diffusivity is very fast, so it helps in the extraction at a faster rate, and that is why the supercritical fluid technologies can be operated in the static mode as well as in the dynamic mode. That way, it helps in the continuous extraction of the specific material or maybe specific component from the food matrix as well. So now, if you just to make you briefly understand about these, how it can selectively extract the compound from the food matrix. So I have just tried to explain in this particular form here. If you try to see this particular box, right? So in this particular box, there are particles which are yellow, and then saffron color particles are also there. And the blue color one indicates the solvent, which is a supercritical stage of the particular solvent, that is a CO2. Okay. So CO2, because if CO2 once it reaches to a supercritical stage, as I mentioned, because of this higher diffusivity into the food matrix, it dissolves the substances very easily in this particular solvent, and then it resolves this analyte from the matrix. That means it will take away those particular analyte from the matrix, and then it will come out in this particular way. And once it come out of the reactor, once it come out of the reactor means what? I am going to release the specific compound which I wanted to extract. So for example, here I want to extract only these yellow particular points and not the saffron one. Okay. So I have to tune this particular property of the CO2 in such a way that it will only extract these yellow spotted compounds and not the saffron one. And because of that, this kind of extraction gives very high selectivity as well, right? So this CO2 plus dissolved analyte, it can be trapped in the solvent, or once you release this pressure here, the CO2 will get released in the form of CO2, and then they will just separate out this particular analyte from the CO2, so that you can get a very pure form of this analyte here, or you can say the pure form of the compound here. So because of these favorable transport properties, it is desirable mostly in the extraction operation that the transport property should be favorable to the extraction medium. So that is what is the role of the supercritical CO2 here. And the low viscosities, it facilitates this penetration of this supercritical CO2 into these particular particulate beds, I would say, and reduce the power requirement in transferring this particular fluid through the system as well. Because once it is diffusing, it will try to once, because see, for example, this blue arrow shows the CO2. Once I have gone purging this CO2 from this particular end inside this food matrix, so they will try to penetrate through this particular pores of the food matrix, will extract these, and then the newer molecule will try to take the space of the older CO2 molecule, and because of that transport, the older molecule will try to come out from this particular matrix here, and then the newer will try to take a space. because of that, the continuous extraction also can be, that is, I would say, in the dynamic mode, the extraction can be carried out in the supercritical CO2 stage. And in some cases, what happens is like I will just put the CO2, the required amount of the CO2 here inside this particular chamber, along with the food element which are need to be used for the extraction of the compound from the certain biomaterial which need to be extracted. And then I will just close the vessel and will go on increasing the temperature and pressure. So once it reach to a supercritical stage, I will maintain that particular stage for the 30 minutes. And once the 30 minutes are over, like 40 minutes are over, I'm just giving the example of 30 minutes and 40 minutes. Based on the extraction timing, you can always change that particular time as well. And then I can just release the warm. So during that particular time, the static phase of the CO2 and the material was interacting with each other, and the extraction was happening in that particular scale. Okay. And once I release that particular gas now, the CO2 will come out from the particular reactor along with this analyte now. So dissolved analyte, I would say. And once it comes out, I can dissolve this in the specific solvent, which is an environment friendly solvent. So this yellow dotted compounds will get dissolved in that, and the CO2 which is not soluble in that solvent will come out from the solvent automatically. So that way also you can do the extraction of the materials or component using this particular fluid stage. So, for example, here, as you know, this is what I told earlier as well. This is called as a trapping of the solids in the specific medium here. So, once this particular compound along with the CO2 and analyte enters into this particular blue, you can say here the solvent which should be soluble in this particular, the compound should be soluble in this solvent, that kind of solvent you need to select here. And hence, once it gets solubilized, automatically the CO2 will get released from this particular compound, the yellow points here. And then this CO2 will get released out automatically from here. So this is how this trapping of the selective materials can be done in case of the supercritical CO2 as well. This I will just show you also in one of the slide how you can do it very selectively. So favorable transport properties of the CO2 means the low viscosities. It facilitates the penetration of this supercritical fluid into the particulate beds and reduce the power requirement in the transferring of this fluid through the system. And because of the gas-like behavior of the supercritical fluid, the diffusivity increases, and it increases the mass transfer as well, and approaches. And once it, because say for example, if I am allowing this supercritical CO2 and the material to be extracted to reach to the equilibrium, so what happens is like during that stages of approaching the equilibrium stage, so most of these material which are present in the food matrix will get extracted by this CO2 phase or the substance, right? And once it is getting extracted, I can just simply release this material into another vessel. So once it release it to the another vessel, so that is at a room temperature, I would say, or normal condition rather than room temperature. I will mention the normal condition. So once it reaches to a normal condition, the liquid CO2 basically becomes a gaseous CO2, because at the normal conditions you cannot liquefy the CO2. CO2 liquefaction can be done at a relatively lower temperature. You need to bring down a temperature of even like -5 or -10 degree, then only you can liquefy this particular CO2. Okay, so once it reaches to a 30-degree temperature, basically it's nothing but a gaseous form. So the entire CO2 will come out from that particular matrix, and it will just separate out the your analyte very easily. And that is why by doing that, it increases the extraction efficiency of the material, this particular process as well. So I hope all are able to listen to me.
Yes, sir.
Okay.
Yes, sir.
So once you see the equilibrium, uh, it is expressed by the basically in terms of solubility of the component at a given temperature and the pressure, basically. Okay. So there are three main rules to be applied for this supercritical CO2 technique here, because what happens in case of the solubility of the lower molecular weight, or you can say the low polarity organic compounds, like say for example carbohydrates, alcohols, carboxylic acid, esters, aldehydes. they are having basically a low polarity. Okay, and it's very high in the supercritical CO2. Because of that, it will get extracted very easily. Because supercritical CO2 basically is a non-polar range. It behaves like in the non-polar range, and these are completely miscible and gets extracted very easily from this kind of the materials. So the macromolecules like high polar molecules, sugar, starches, proteins, salts are not soluble and hence remains into the food matrix. So basically, if you want to extract a specific ester molecule from any substance here, which has a mixture of like sugar, starch, proteins, so you can easily extract these esters using this particular technique because others will remain untouched even of non-solubility of this particular material in the supercritical CO2, right? So basically, it will just take away the esters, and that is what I have shown the example of the saffron and the yellow particle there. So basically, the saffrons are nothing but your sugar, starch, and the proteins, and your yellow the particles are nothing but the esters. So basically, it will just take those esters very efficiently along with it and solubilize it, and then it will try to take out all those esters from the food matrix or that particular compound, right? So that way, it plays a very good role in terms of solubility and the solubility of the some insoluble components. This can be increased, but then this is an alternative. Suppose if you want to extract esters along with, say, for example, the proteins. Okay, so that can be also done, but then it required some alteration or maybe you can say some fine tuning of the properties of the supercritical fluid. But then by doing so, you also need to add a co-solvent to it, that is also called as the entrainers, such as in terms of ethanol and the acetone, so that you can because as I told you, these particular molecules are not soluble. So to make it soluble, because these are polar, so you need to tune the properties of the CO2 in that way, right? So that it will be slightly moving towards the polar range, and then it will take away because CO2 as a non-polar, ethanol as a particular compound which will try to take away these proteins, it will try to get extracted by both the ways. So that need to be done by using a co-solvent. That's why it is called as a co-solvent somewhere in the literature, somewhere it is called as the internals also. So both the terminologies are nothing but the same. So for example, now just to brief you about this example of extraction, if you are looking for the beta carotene, so the solubility of this beta carotene, it is increased to a great extent by using a mixture of supercritical carbon dioxide and the ethyl acetate. Because here ethyl acetate is acting as a kind of a co-solvent. If you try to do it only with the supercritical CO2, you may find that the entire beta carotene may not get extracted. So because of the nature of the slight polarity. So once you add another co-solvent to it, so it just fine tunes those properties of the supercritical fluid, which also helps in the extraction. And normally used internal is nothing but mostly the ethanol, but sometimes the ethyl acid is also being used for the extraction of the compound. So the superior product quality in the sense is like uh, this particular technique can be used to extract the compound with a delicate way, and also it helps to maintain the freshness which is close to a natural compound, because we have not added any kind of solvent to it, and whatever the solvent which we have added, it got evaporated during the course. So because of that, you won't find any traces behind the behind in the extract also. So that is what the meaning of it, like it mimics to the freshness close to the natural material as well, and high concentration of the desired active components with no residual solvent. That is what I told, like you can increase even the concentration of this desired active component by fine tuning this particular properties of the supercritical fluid. And longer shelf life is a very important point because of the free biological contaminants. So this is a very effective uh, point here, because this particular extraction also helps to increase the shelf life of the product. Okay, so as because of the it is not contaminated by any kind of the microbial contamination, and because of that the shelf life found to be very high, and that also we observed in our studies here that the shelf life has increased drastically when you try to use this kind of solvent for the extraction. Superior process in terms of the simultaneous fractionation of the extract is possible in the single step that I will describe you in one of the slide down. What is meant by the fractionation and the extraction in one cycle, or you can say in the single step. That is also possible to do in case of the supercritical CO2. Fractionation in the sense is like why it is called as a fractionation. Say for example, I give you the example of extraction of the esters and the protein in one go. That is nothing but in the one step. But then obviously when I'm trying to extract this, although I'm trying to extract it both together, but when I'm trying to do the fractionation of it, I want both this material to be in the separate vessels once it comes out, right? So that is possible to do using this fractionation here because as you know, these both the compounds are different, right? The ester is having some properties, the protein is also having some different properties, and because of that, because of the solubility difference in solubility also, this material got solubilized into this particular fluid automatically. So automatically once I change the temperature in the fractionating vessel, so the specific material is only will get separated out because the solubility of that particular material is not possible to be remain there beyond that particular temperature and pressure. So basically it will get separated out automatically from the gaseous CO2. Whereas if the protein has a still higher solubility, it still remains in that particular solvent unless it reaches to its specific temperature and pressure where its solubility is no more in the CO2. So that way also the fractionation is possible in case of this particular technique. And the flexible operating conditions for the multiple product extraction, as I give an example of esters and the protein, you can extract the multiple product as well. But then in that particular case, you require the provision of the fractionation in your system that you should fractionate those particular compound automatically. Carbon dioxide as a solvent is regarded as a gas that is generally regarded as safe for the food products. Technical disadvantage is only that we require relatively high pressure, but then 72 bar is not that high pressure. And then the low polarity of the supercritical CO2 solvent. Because of that, most of the time you may not be able to extract the compound of the choice. And for that reason, there is a provision that you can do the alteration by using the co-solvent so that you can change this polarity of the CO2 as well. So this is what I was talking about, the system component here, that is SCP component here. So for example, if you are using the gaseous CO2 in the form of like cylinder, if you have, so you can use this particular CO2 from the cylinder. So in between, because I have not shown the particular uh, chiller here, so it will just pass through a chiller first so that the CO, gaseous CO2 can be converted into a liquid one, and then it will be pumped using the CO2 pump, right? And it will be pumped into the chamber that is called as the extraction chamber. Now, if you want a modifier here, that is called as a modifier pump. So sometimes if I am not using modifier pump, I will directly inject this particular CO2 inside the extraction chamber. But if I require to use a particular modifier that is called as an internal also or called as a co-solvent also. So then that co-solvent I will put it in this particular co-solvent chamber will be here, and then it will just take this particular this pump will take this modifier and it will mix with this particular CO2 line, and then this will go in combined way inside this chamber, and then because the temperature and pressure of these two solvents are more or less having a similar nature, so it will be in the stage of the supercritical one. But uh, there is one point to be noticed here. If you just go on increasing the percentage of this co-solvent here, because marginally you can put close to 5 to 10%, even less than 10% also this modifier in this case. If you go on increasing this particular percentage, then basically you are disturbing the supercritical stage of the CO2. Okay, because if it, then it is going more into a modifier rather than the CO2, and hence because of that maintaining the supercritical stage of the CO2 will be very difficult in that case. So that need to be taken into consideration. And once the extraction is allowed to take place in this sample chamber here, so after extraction, it can be passed. This is what I was telling you about the trap. solid in the liquid stage here. So we can just put particular entire material in this trap solver. So in this case, if you see here, this blue are nothing but act as a kind of a CO2. These blue bubbles here are acting as a kind of a CO2 molecule, and black is nothing but your product of the interest. So once it reaches into this, now it is a normal temperature and pressure. Because of that, this liquid CO2 is becoming a kind of a now the supercritical CO2 is becoming a kind of a CO2 at a normal temperature and pressure, and it will just bubble out from this particular matrix or maybe from this trap, and just it will just leave this black compound inside this particular trap here, because these are no longer soluble into the CO2, because it has reached to a stage where the solubility of the CO2 in this particular black point is black spot is negligible. So because of that, it is just I would say separating out. Okay, and that way it becomes very easy to separate this particular compound, and this is how we do the fractionation of this particular compound as well. So this method can be operated in the two way, as I was talking about the static mode and the dynamic mode of the system. The static method means uh, it carries out the entire process at the equilibrium. Okay. So that means what is the meaning of this? What happened in case of the static experimentation here? So there are two distinct steps in this particular process. First, the mobile phase feeds the extraction cell and interact with the sample. The mobile phase here is nothing but you are the supercritical CO2 which is getting injected inside the sample chamber. And then the wall and the second pump is open, and then the extracted substances are taken out at a once. So means once the interaction is allowed to take place for a specific interval of time, say for example, as I given 30 minutes, 40 minutes based on the extraction efficiency. So once it is done, then the wall and the second pump is open. So once you open that, so the extracted substances are taken out along with this particular CO2. Okay, so that is called as a static mode. Once I go for the dynamic mode of the extraction of this particular compound, so in this case, what happens is like the second pump is sending the material out to the collection chamber, is always open during the extraction process. So once the CO2 comes inside the chamber, so we maintain the flow of the CO2 in such a way that it will have a certain residence time inside the chamber, and then it will come out automatically during the from the other opening from the other end during the extraction process itself. So here the mobile phase reaches the extraction cell and extract the compound in order to take them out consistently. So this operation continues in this particular way. Okay, but here the food matrix is in one chamber. The CO2 is just flowing through it and then extracting it and again coming out from the particular chamber, right? So that way you can handle this dynamic mode of operation as well. So in this case, what happens is like once we introduce the feed in the extractor, that is because the solid feed. So the formation of this mobile phase is nothing but the mixing of this solid with the supercritical fluid. So once it happens, so the exposure of this mobile phase to pressure of around like 50 to 500 atmosphere and the temperature to about 300 degrees C or near to about the critical point. Once it reaches to that particular phase here, then it reaches to the solvency power of the supercritical fluid so that it can extract the compound very easily. And then the isolation of this dissolved solid by the precipitation, as I shown the example here, you can precipitate in this particular way in the trap here, right? Basically, you are precipitating the material here just by removing the CO2 out. So the application of the supercritical fluid extraction in the food, there are a lot of applications. We cannot count even like, but then just to give you some glimpse of it, I've just given two example here of nothing but the caffeine and then the oleoresins extraction. This we already done in our laboratory. That's why we have given the example of the oleoresin extraction from a specific material, that is gingers, which are very endemic to this particular part of the country, that is northeastern region of the country. So we have taken that as a one component for the extraction. So the decaffeination is largely carried out using the supercritical CO2. Okay. So one another part is nothing but the extraction of the oleoresin from spices, and then again fractionating it into a fixed and the essential oil component As you know, yeah, this is a very good point. I can give you the example of the fractionation here, because when you try to extract this oleoresin from any kind of a spices, it is very difficult to get only essential oil along in the extraction. Sometimes you also get the fixed oil. Okay, but now if you want to just separate out the essential oil from the fixed oil again, you need to go for the second downstream processing operation. But if you are using the supercritical CO2, then you can do it very easily in the fractionating chamber itself, because the solubility of the fixed oil and the essential oil in the supercritical CO2 is at different temperature and the pressure. So once I adjust the temperature of the fractionator, where I have to just separate out the essential oil, I can adjust that particular temperature and pressure so that the essential oil will get separated out from the CO2 and the fixed oil, and then the fixed oil and the CO2 will go to the next chamber here. Okay, and then once I maintain the specific temperature and pressure where the fixed oil will get separated out from the CO2, so obviously the CO2 will separate out from the fixed oil as well, and then you can only get the CO2 out of it. So that way also, so this fractionation can be understood very easily in case of the supercritical CO2. The supercritical fluid method using CO2 as a solvent can reduce the wastewater compared to the traditional mechanical extraction, because and this is very common example nowadays for the extraction purpose, because there is no role of water in the entire processing here now. So wastewater generation is very minimal using these processes. Sometimes these kind of methods are also being used to extract the polyphenols, the pigments from the waste fruits, the waste flowers, the vegetables, right? So these are very well-known examples in the case of extraction now. So what are the advantages of this supercritical fluid extraction over the solvent extraction? Uh, as you know, there are multiple advantages, as we have discussed many of these advantages in some of the slides as well, because it replaces the organic solvent. That is one of the most important points is here, and also the complete and the easy recovery of the solvent from the extract or the raffinate. This both is possible in this case. Okay, and this is a very rapid process. You don't need to continue the process for 8 hours, 10 hours just to reach to a equilibrium of the extraction. Here, that equilibrium can be reached very faster rate because of the solvency power of the supercritical CO2, and can be used as a continuous process as well. That is also possible in the supercritical CO2 stage, suitable for the extraction and the purification of the low volatile components, as I given the example of the essential oil from the fixed oil. So that is also possible here in the supercritical CO2. But this may not be possible when you try to use the hexane, because once you try to use the hexane, the essential oil and the fixed oil will come together in that. And again, you need to go for the separation, that is called as the downstream processing further by using any mode of separation, that is distillation, or maybe you can use it by some kind of membrane process and all, but that is essential. But that can be minimized using the supercritical CO2. It has a low handling cost, yes, because the system is automated, so the handling cost is very minimal in this case. But no doubt, the initial investment cost is relatively high. Okay, even suitable for the thermal sensitive compound as well, that is natural products. Selectively extract the targeted compound, as I given the example of the saffron and the yellow spotted particles. So selectively you can just take out the yellow one, leaving behind the saffron particles behind. And it's a versatile technology in terms you can use it in the wide field of application as well, not limited to the food also. We are using this supercritical CO2 for other applications as well. But some precautions need to be considered or taken while doing this particular process, that you need to provide the adequate time of contact of the solvent with the substance, or maybe the solid particles which are under consideration for the extraction, so that the very good diffusion of the solute from the inside the solid particles to solvent will take place very effectively. Because if you won't provide a sufficient time, the extraction may not be the effective one, and the equilibrium should be achieved. This is very important. That need to be studied very effectively in case of the supercritical CO2 technique here, because the equilibrium for each component may not be the same. So that you need to study very systematically using the optimization tools. Either you can do the simulation first using a standard compound, and then you can see the equilibrium need to be what type of equilibrium need to be achieved for this kind of solutes. So based on that, you can plan the experiment as well. So for example here, why use the modifier? So I wanted to just give one small example here because when you see a kind of a triglyceride, it also has a phospholipids present in it. So when you try to extract only a triglyceride molecules from these, but along with that also you require phospholipids to be present in that. So what happens is like suppose this R1 and 2, suppose which are basically a non-polar compound, but this R3 in that case is nothing but a slightly a polar molecules. So if you have to extract these together now, so you need to make use of some kind of modifier. So that's why it will take away along with one and two as well as the three together. Otherwise, this will remain into the you can say the substance as it is without getting affected. So by that way, otherwise this triglyceride will get extracted very effectively, but this will remain because of this polar nature of this particular in the this particular group, right? So for that reason, this fine tuning is required so that you can take away these two entities together from the substance. So as I given the example, like the co-solvents that are always added to CO2 to enhance the extraction efficiency, but then you please make sure that the percentage of this co-solvent should be limited to up to 10%. But even I have referred not to exceed to even more than 8% also because we tested these and once it reached to a 10% and so then we always see there is a change in the critical nature of the CO2 as well. This we have experienced from our experimentation as well. And then basically it affects the extraction efficiency as well as the extraction yield. So just to expand the extraction range to include the more polar lipids, so you can add these kind of solvents here, but make it limit to it. Sometimes we see that sometimes people are referring to 20% of the solvent, but then it never called as a kind of critical state of the substance now because it has already diluted that particular critical stage now. The organic modifiers can always increase the complexity of the experimental model, and that determines the supercritical CO2 extraction pattern. And that's the reason I mentioned when you try to add this kind of modifier, so it increases the complexity of the supercritical nature of the particular substance altogether. So that's the reason the percentage should not go beyond this range. Apart from that, as I told, this particular technique is being also used to formulate the microparticles as well. It also used in the drying, in case of reaction, in case of cleaning, water oxidation system as well. But then we try to make use of it for the particulate formulation here. How we can do it is like you require for that purpose a RAS, that is called as a rapid expansion of a supercritical solution. So you have to expand this particular solution at a very rapid rate so that it will form this kind of a nano powder inside the chamber. So what happened in that case is like any active ingredient which need to be converted into a kind of a nano powder that is in the encapsulated form basically. So we try to use this RAS system for that. Otherwise, normally if you are just trying to do the extraction, so we use a normal extraction technique. So what happened in that case is like this nozzle here has a kind of a you can say this nozzle is a basically a diamond nozzle, so it handles a very high effective high temperature and pressure as well, and you won't get affected by that particular pressure and temperature. So when you purge this CO2 inside this active ingredients, so this CO2 will take away along with it this active ingredient, and then it solubilize this active ingredient, and once it reaches to in this particular chamber here, so what is happening is like we are doing the rapid expansion of this particular solution. So once you do the rapid expansion, so the CO2 will get separated out from this particular powder. And then whatever the soluble ingredients were there along with this particular CO2 will get separated out easily in the form of this nano powder here. Okay. So because of this rapid supersaturation, what happens is like it forms a fine and the monodispersed powder inside this particular chamber here. It will be very fine nanoparticles you can also achieve based on the diameter and the size of the nozzle here, which is shown these yellow spots here. So based on that, you can basically change the size of this nanopowder as well. So this we tried with some kind of oleoresins encapsulation in our lab as well. And the supercritical anti-solvent technique is one technique here which is being used as I given the example of the organic solvent. Sometimes We can also use the organic solvent which are required along with the active ingredient, because some active ingredient which are even soluble in the organic solvent, so that can be used in this case. And then we can also prepare use the fine nanoparticles using this kind of technique as well. That is called as a SAS, that is active anti-solvent, supercritical anti-solvent, and this is called as a expansion of the supercritical solution, that is called as a RES and the SAS in the supercritical system, which is very commonly used technologies. So this is about the supercritical stage. I will just quickly I will just show you the what are the work we have done in our lab in 1 or 2 minutes. As I told you, like when you have to do the fractionation, how to do the fractionation here. This shows the volatile oil, and this shows the fixed oil, that is oleoresin, which can be extracted from the ginger here. So we have optimized the entire process here, and which we have scaled up even to 40 folds than that of the lab scale, using the commercial operation in one of the industry in the north. And then if you see here, this is basically an extraction vessel. The entire extraction is carried out in this particular vessel. And once it reaches to a first fractionator here, so now I can tune this temperature of the fractionator, where we can put the pressure of 175 bar and the 40 degrees C. Okay, and we can now tune the temperature and the pressure of this second fractionator here, that is 40 bar and the CO2. So what happened in this case is, like, because what we observe at this pressure and the temperature, this oleoresins is no longer soluble into this particular, because when you have done the extraction, we have done the extraction at a 275 bar or 276 bar, where the oleoresin is easily soluble into this particular supercritical CO2 stage. And once it reaches to this particular bar pressure, that is 175 temperature, so this oleoresin is getting separated out from the supercritical CO2. But essentially, the volatile oil still remains in the CO2, because at this pressure and temperature, the volatile oil is still soluble into the CO2. So then we passed on this to a second fractionator, where we maintain the temperature of 40 bar and 40 degree. So at this stage, the volatile oil is no longer soluble into the CO2. It gets separated out automatically from the CO2, and then you can just only get the CO2 as a gas from this particular top machine here. By that way, we could achieve the yield of around like 6% of the oleoresin and 2.8% of the volatile oil yield using this particular technique. Although commercial hexane use yield of around like close to 3.2%, but then the purity matters a lot. Here we are getting a pure volatile oil and pure oleoresin of 96%, even 95% of the purity it can be achieved with 51% of the ginger oils in these oleoresins, which is potential compound in the oleoresin of the ginger. That is, you can see the mixture is having this here, and once you fractionate it using this technique, you can separate out volatile oils and the oleoresin. So this we have done at the commercial unit, commercial scale unit. Okay, and this is what is the advantage of this particular technique. You don't need to go for the separate separation technique, downstreaming of this particular one. And this shows like further, if you want to extract in the multiple way, we can go on increasing this fractionator here. You can change the temperature and pressure accordingly. You can just separate out the compound, and that is what we have done. The first separator, second, accordingly we have done this separation, and we could achieve a very good separation of the volatile oils as well as the oleoresins. Now, if you see this particular chart here, which shows the fractionated volatile quality. Now, if you try to see here, the ciskosterpene is there here. Then the zingiberine is also present in this one. So supercritical CO2 one and the steam distill one, because we have compared this with the steam distill compound as well as the supercritical CO2. This is done in our lab only, steam distill as well as the supercritical CO2. This is the work of one of our PhD student work. So you can see here there is a significant jump in the extraction yield of these compounds in the using supercritical CO2 as well. Okay, obviously the retention time is changing with the change in this particular extraction yield of the specific compound. Similarly, when you try to do it with the oxalate using the hexane and the ethanol and the acetone, still we could not reach to that particular yield where the supercritical CO2 has given a very high yield of this particular compounds, that is 6-gingerol, and the uh, uh, in the dry ginger basis and the in the basically on the extract basis also, if you can see, is a good increase in the yield of the particular products. Similarly, we have extracted the citronal oil because this is very widely known oil, that is citronella oil from the citronella grass. So this also we have studied, but this we have done using the supercritical water technology, not with the supercritical CO2. And surprisingly, we could able to extract this citronellol, gerinol, limonene, and the linalool very high with a very high quantity using this supercritical water technology and without having any disintegration of this product. So it was the product was remain intact as kind of its natural product even. But although we have not done in the supercritical stage, we have done at a subcritical water technology. We have not reached to this particular critical point here. Below that point only we try to do the extraction because of the thermal nature of the particular compounds. We did not study at a higher temperature range. So this is just the experimental setup. I wanted just to show you like how we did it in the water stage, because for CO2 it is different one as we know. So once you see here, this yellow part indicates the solvent plus solute together, and once the reaction continues, the extraction happens, and then we try to purge the inert environment in this particular reactor, right? Then the gas, like you can see, the gas comes out here from here, and then it pump the sample out. We can collect the sample here and we can analyze intermittently how the reaction is happening in case of the supercritical water as well. So that way also we have studied this particular concept in our case. Okay. And these are just experimental part of it. I will not go in detail of that because this is very widely a published literature available in the uh, most of the journals now. Similarly, we have done the supercritical water with the bamboo biomass to extract this component like cell bios, glucose, xylose, this kind of compounds also we try to extract from the bamboo biomass using supercritical water technology. That also we have done in our laboratory. So as I mentioned, the scope is not limited. We have wider application of these technologies for the different applications, not limited to only the food. You can go for the other applications as well, and these are indicating some references and acknowledgement to our past student from the lab and the DBT and DST for the financial support in terms of projects. Our collaborator, Professor Naik from IIT Delhi and Professor Raut from CMAP Lucknow, who helps us in analysis of some of the compounds regularly. Professor Naik helps us in some kind of like technical advices in case of supercritical technology whenever it is required. And thank you for your attention. And I hope I could able to reach to the audience with this talk. And if you have any queries about this talk, I will be free to answer. I'll be happy to answer to your queries as well. Thank you. Thank you once again.
Thank you, sir.
And I hope I
Uh,
could able to the time limit as well.
yes, sir. Uh, any questions? Anybody? Okay. So
No, that's
thank you
it.
very much, sir, for given informative, knowledgeable session to our participants. And I hope all participants will be explore knowledge in their research work as well as future work. Thank you. Thank you, sir, once again.
Well,
Uh, hello. Uh, uh, Dear participants, please uh, on your camera for a one group photo.
Actually, somebody has posted a question, I guess, about the CO2 non-polar nature and then polar course alone is necessary. Yes, as I mentioned in the one of the slide, like why you need to tune the properties. So that is one of the main thing that if you want to extract some kind of substance which has a slight polarity, then obviously you need to add a kind of modifier in it. So that is essential. But then, as I mentioned, the percentage of modifier may not be too high. You can limit it to a very low value as well. A percentage of like 5%, even it is sometimes sufficient to tune the properties to make it slightly polar in nature so that it can extract the polar materials.
Okay. Okay, sir. Thank you once again.
Okay, thank you. So may I leave now?
Group photo.
Sir, please make camera is on. Then we will take one group photo, sir. If thank you, sir.
Thank you, sir.
Take photograph. आगे सर का
Hello.
Yes, sir.
Yes, sir. Sir, one more question is on chat box. What about the scalabilities of SFE?
Scalability already actually the commercial operation of the supercritical fluid extraction is happening. So scalability is not the issue in case of supercritical fluid. There are industries which are already working on the supercritical fluid extraction at a commercial scale as well. Okay, so scalability is not an issue in case of supercritical fluid now.
Okay, sir. Then
Yeah.
thank you, sir. Thank you very much.